We'll start now then, if everybody's ready.
So I'm Nicolas HANUSSE, so I'm the president of a jury. So we'll start in 2 minutes now. I will present you the jury for the defense of Jason Schoeters. So Paola FLOCCHINI is a professor from University of Ottawa. Rolf NIEDERMEIER is also professor, but in the Technische Universität of Berlin. Eric SANLAVILLE est professeur des universités à l'Université du Havre, en France.
English.
Et puis, nous avons également dans le jury, sorry, and we have in the jury, Ralf KLASING, myself, so Nicolas HANUSSE from University of Bordeaux, and Arnaud Castet. So, Jason, you have roughly 45 minutes to present your thesis.
Okay, thank you very much. Thank you very much. So let's start. Maybe I can take off my mask as I'm pretty far away from you. So my name is Jason Schoeters, and I'm here today to present, or rather defend, my PhD thesis entitled Contributions to Temporal Graph Theory and Mobility-Related Problems. So this is a thesis I started 3 years ago under supervision of Arnaud Castet. So let's start with a little bit of context first. So over the last few years, temporal graph theory has gained in interest, and I think this is due to the fact that temporal graphs can represent a wide variety of different settings. For example, the default setting would be maybe computer networks. And so here temporal graphs can represent, for example, faulty networks with maybe some errors or some package loss. But it can also represent highly dynamic systems, such as maybe a swarm of drones. Or more recently, it can also maybe represent a population which interacts with each other, so as to maybe understand the spread of a virus, for example. And so two of these examples, namely the swarm of drones and the population, can be seen as a group of mobile entities. And so we're interested in this type of temporal graphs because, as you can imagine, if you have some control over the mobility of these entities, then you may have some impact on the connectivity, let's say, of the temporal graph. So for example, if you are able to enforce social distancing, for example, on the population here, then you can obtain low connectivity in the underlying or the induced temporal graph, or even no connectivity at all. On the other end, if you enforce periodic meetings, such as work-related meetings or school, or you go to see some family every weekend, then the underlying or the induced temporal graph can have a high connectivity, even a periodic connectivity between entities. And of course, you can have something in between, so not completely unconnected, but not completely periodically connected. Maybe you can select one entity, which then goes and visits from time to time other entities. So before you can ask the question of how to control a group of mobile entities so as to have some impact on the underlying or the induced temporal graph, you may ask the question, how do I control an entity with some mobility constraints at all? How do I even control one entity? And so this area of research is mostly known as motion planning. And so motion planning has a wide variety of applications, from the minimization of energy consumption, so as to explore, for example, dangerous terrain or even hostile worlds. And you can also maybe create some bots. For example, in a video game, you can have maybe a bot which follows around the character. So this can be done through motion planning. And maybe another example, you can have competitive racing, such as maybe drone racing. So this is an image of a drone race. And so last time I checked, so a few days ago, human players were still able to beat AI-controlled bots in drone racing. And so maybe you can ask yourself the question, well, maybe there's still something we don't really understand in how to control or optimally control a highly mobile entity. And so my thesis is mainly interested in these two big domains. So on one side, temporal graph theory, and on the other side, motion planning. And so you can see that there's a little bit of an intersection here. And so we were interested in both domains as well as the intersection. And so before presenting our contributions in this thesis, I'd like to maybe give some examples of what you can find in temporal graph theory. So in temporal graph theory, there's always the ever-present problem of coloring a graph, but this time in a temporal setting. So this may represent maybe some antennas with different wavelengths. So you can also find some other problems, such as min cost flow problem, which was studied recently in temporal setting. On the other end, you can find in motion planning this time, graph search algorithms, such as BFS or A*. And you can also find maybe a little bit of control theory. As the intersection, you may find some subjects, such as maybe graph exploration. So you're given a temporal graph, and you would like to explore this temporal graph with the aid of little robots that you put on the vertices. So our contributions are the following. Oh, there's a little error. Just to the, okay. So there was a little technical problem here, no problem. So our contributions are the following during this thesis. So we mainly have three large contributions, which are grouped together like this. So one in every part of these domains and one in the intersection. And so I will follow the same order as I presented these in the thesis document. So I will start with temporal clicks admitting sparse spanners. And then we'll go on to vector TSP. And at the end, we'll talk a little bit about mobility models. So the first part of this thesis is heavily based on work with Arnaud and Joseph Peters. And so this work was published at eCalp 2019. And recently currently we're under minor revision for JCSS, for the journal version of this work. So I've been talking about temporal graphs since the beginning, but what exactly is a temporal graph? Well, a temporal graph is an abstract model which can modularize or represent a wide variety of situations, such as I presented before. But most of the time, we like to represent it as some dots with some links in between, and we call these dots vertices. And these links, we call these, well, either links or edges. And the temporal graph is when these edges appear and disappear over some lifetime of the given graph. So for example, we like to represent these as such. So there are other representations, but this one is a rather compact one. So on every edge, you put some labels representing the presence of this edge over time. So for example, this edge over here is present at times 0, 1, and 2, but not at 3. So this edge is present at time 3 as well as 2. So another representation of a dynamic graph can be given like this, just as a sequence of static graphs or standard graphs. And each standard graph or each static graph will then represent the temporal graph at a given time moment. For example, G2 over here represents this temporal graph at time step 2. And these are actually the same graphs, just represented differently. And now in this temporal setting, you can define the concept of a temporal path. So the analog of a path in static graphs. We often like to call this journey, but some people also call this temporal path. And so this is a path with non-decreasing time labels on the edges. So for example, this marked in red is a journey because this is a path in the temporal graph, but over time, as you can see, first we use this edge at time step 0, then at time step 1, this edge. For some reason, we don't use any edges here, that's allowed. And then we use this edge as a last edge of our journey. So this journey is present over here as well, of course. And now a temporally connected graph is defined as a temporal graph in which there exists at least one journey between every pair of vertices. So here I just said that this vertex can reach this vertex over time through a journey. So you may think, well, is this graph temporally connected then? But the answer is no, because there exists no journey in the other sense. So from this vertex to this vertex, there actually is no journey. So how can you construct a temporally connected graph? Well, there's a simple way to construct a temporally connected graph. You just take the complete graph, so all the edges, and you just put some time labels on these edges. And now this graph is said to be temporally connected because whenever you would like to reach some other vertex, so if I'm over here and I would like to reach maybe this vertex, then I just have to wait for the edge between us to appear, which will appear at time 12. Final definition, the one of a temporal spanner. So a temporal spanner is a subset of edges which preserves temporal connectivity. So if you, in other words, if you take some temporally connected graph, then you may be able to remove some of these edges without breaking temporal connectivity. For example, this edge may have been removed, which has been removed. All the dashed edges here are removed, and all the bold edges are the ones that remain in the temporal spanner. And so indeed, this edge may have been removed because, well, it's not necessary for the temporal connectivity between this vertex and this vertex, because this vertex can still reach this one through journey 6 and then 8 over time. And the reverse is true as well. This vertex can reach this vertex over time through the journey 4 and then 11. Now, as a context, you may see this as some people who have some gossip they would like to share, and they also would like to be aware of all the gossip in say, a community. And so maybe they arrange some phone calls between every pair of people. And so a temporal spanner may represent a way to reduce the number of phone calls. And so this is not just a context taken out of nowhere. This is actually from, this concept of temporal spanner is actually very close to gossip theory. And some lower bounds from gossip theory apply to our problem of temporal spanners. So why are we interested in temporal spanners? Well, mainly because almost 20 years ago, Kempe, Kleinberg, and Kumar asked the following question in one of their papers. So given a temporally connected graph, does there always exist a sparse temporal spanner? So they asked their question, and a few lines afterwards, after the question, in the same paper, they gave a counterexample. They said, no, in all generality, for any, in the general case, you can actually construct a counterexample of hypercubes in which you label the edges in a specific manner such that no edge can be removed without breaking temporal connectivity. And so they weren't really satisfied with this counterexample because hypercubes, are not very dense graphs to start with. So maybe you don't have enough room to find a sparse temporal spanner. And so they left the question open for dense temporal graphs. 14 years later, Axiotis and Fotakis answered this question for dense temporal graphs with a negative answer. So again, there's a counterexample, a bit less trivial than the hypercubes, in which you cannot remove any edge without breaking temporal connectivity. And so this is a dense graph. So the dense part is here at the top, but it's hard to see. And so you may be wondering, well, okay, the result for general graphs is over here. The result for general dense graphs is over here. What is there left to do? Well, one thing you can explore is maybe the densest of graphs. So maybe a temporal clique, if you consider any given temporal clique. Now can you maybe find always a sparse temporal spanner? So this is the question we are interested in this part. And it turns out that yes, you can always find a sparse temporal spanner for temporal cliques. And so I'll show you how to construct one. So we start with constructing the forward fireworks. And you'll see why this is called this fireworks in just a minute. So let's start by constructing it. And afterwards, I'll tell you what this is all about. So to start constructing the forward fireworks, you take your input temporal clique. And for every vertex V, you consider the locally minimum edge. So for example, for this vertex V, its locally minimum edge is the one with the label 3, because 3 is smaller than 6, 8, 7, and 10. And you do this for all vertices. And what you obtain is, so you select it, you give it some color, so here green, and you give it some direction, okay, so towards the vertex. And what you create are journeys. Look, there's one journey over here, and there's another one over here. And now at the end of these journeys, you give a special name to the destinations of the journeys. We call them emitters, because for every emitter, afterwards, we select all of the outgoing edges which do not already have a color or a direction, which is done over here. And so now what you do is you take all of these edges which have a color and a direction, you remove the color, you remove the direction, and you can actually prove that the result of this gives a spanner of size essentially 3/4 of the initial edge set size. So in other words, you removed 1/4 of the edge set size. Let's continue. So let's now construct the backward fireworks. So the backward fireworks are essentially the same idea as the forward fireworks, except now we're interested in locally maximum edges. So again, for this vertex over here, its maximum, locally maximum edge is 10. And then we're interested in the sources of the created journeys, so not the destinations, which we call collectors here. And they're called collectors because we select all incoming edges which have not yet been selected around the collectors. And so through a similar argument, these backward fireworks actually produce spanners of, again, size essentially 3/4 of the initial edge set size. So now what we do is we combine both of these fireworks, so which is what I tried to show over here. So it's a bit of a mess. There are some edges which have multiple colors. So there's even one node over here or one vertex which has 2 colors, but that's okay, because we're going to remove a lot of these edges. We're going to remove all of the outgoing arcs from emitters, as well as all of the incoming arcs from collectors, except those specific edges which go between emitter and collector. So which was done over here. So as you can see, for example, this edge has been removed. This edge had a color, and it does not have a color here anymore. Now you take all of these colored edges, you remove the color, you remove the direction, and what you obtain is again a temporal spanner, but this time we removed essentially half of the original edge set. Now, what do we do after this? So we constructed our spanner with the fireworks technique, and now what we do is we see what structure we can obtain in this firework spanner. So there's 2 cases. Either there exists a vertex V, which is neither emitter nor collector, which actually is the case in our example we explained above. So you have this vertex as well as this vertex as well as this vertex. So all of the white ones, which are neither emitter nor collector. And through a little lemma, which we call dismountability, we prove that we can actually reduce our given instance by removing one of these vertices, but by keeping in mind that we have to add later on a constant amount of edges into the final spanner. So as you can see, reducing our instance actually produces another clique. So smaller one, but this one is still a temporal clique. And so what we do in this case, we just recurse the fireworks technique. And so either it ends up in case 1 again, and you remove another vertex and you recurse, or you end up in somewhat the worst case scenario, the case 2, in which every vertex now is either an emitter or a collector. So in this case, we actually obtain a lot of structure in the obtained spanner. So if we take the spanner, we put it over here, we can actually prove that it induces a complete bipartite graph with an independent set of n/2 emitters, as well as an independent set of n/2 collectors, so shown on the left and the right here. And also you get some nice additional structure, perfect matchings to represent the locally maximum edges for all of our vertices, as well as the locally minimum edges. And so now, skipping a somewhat lengthy proof, we can actually use all of this structure to prove that there exists a spanner of size at most n log n in this case. So n being the number of vertices that are left when coming into this case. Now continuing, we analyze whenever we go to case 1 and whenever we end up in case 2. And by analyzing these 2 cases, we can actually add these results together, obtaining a final result of a spanner, a sparse spanner, of size at most n log n. And also, this can be found in polynomial time. as a nice little additional result. So again, here's the result. So as a little conclusion, maybe I can talk about the open problems that remain. So there's two open problems, mainly two open problems. So one of them is, are there sparse temporal spanners of size smaller than n log n? So maybe even of linear size for every temporal clique. So this question is still open. And the other question would be, are there other classes of dense temporal graphs with sparse temporal spanners? So this question is still open as well. So that was it for the sparse spanners in temporal cliques part. Let's go on to the next part, which is vector TSP. So as you can see, this changes a bit in terms of the domain. So we went from a purely temporal graph theory subject to a motion planning subject, but both are dynamical systems. So this part is based on work with Arnaud as well as with Mathieu Raffineau. And we recently published this in 2020 at Algo Sensors. And the journal version will probably be submitted maybe in a few weeks, maximum a few months maybe. And so before I can talk about vector TSP, I have to talk about TSP, or traveling salesperson problem. So instead of giving you the general definition, or maybe I can give the general definition. So given n points in the plane, we ask the question, so n points in the plane, or cities, as we often call these points in the plane, we can ask the question, what is the shortest tour visiting all of these cities and going back to the starting city? So I took a little example here, representing the trip I would like to do this summer to visit some family, as well as some friends in Belgium. And so there's 8 cities that I would like to visit, and this corresponds to roughly 5,000 different visit orders. So I have to choose between one of these 5,000 visit orders. And of course, I would like to avoid driving 950 kilometers just to visit all of these cities. So there are some nice little algorithms which give you a rather good result in practice. For example, there's nearest neighbor, which start at some random starting city, say this one, and then you go and visit all of the unvisited cities which are closest by. So you always go to the closest city which is not yet been visited, which results in 200 kilometers less than the other solution. But as it turns out, the optimal solution is the following, at about 660 kilometers. So this one was computed with a TSP solver named Concorde, but for 8 cities, we may have even used a brute force algorithm. But so in practice, traveling salesperson problem is actually pretty solvable in practice, because you have all of these solvers and all of these nice little algorithms. So what is the problem, you may ask? Well, the problem is that traveling salesperson problem does not really take into account high mobility entities whenever they visit some given points in the plane. For example, in a drone race, the drone race I talked about earlier. So if you have some points you would like to visit with a drone, then one of the issues for the given solution tour for Euclidean TSP is that there are some sharp angles, or there may be some sharp angles in a solution. And so you can see this is maybe suboptimal for a drone with high velocity, high acceleration, as well as high inertia forces, because whenever, say, it comes from here, it would have to slow down considerably and then reaccelerate here, which loses some time. So another problem is that all of these tours in Euclidean TSP are evaluated solely by distance and not by time needed to cross this distance. So there is some related work on this problem of adding acceleration to the TSP. So first of all, there's Dubin's TSP. So Savla, Bülow, and Frazzoli worked a lot on these problems. And in Dubin's TSP, you may imagine this is a TSP for vehicles which have a bounded angle on their wheels, such as maybe cars. So cars can only drive in some wide angle when they want to turn. And so this results in a curvature constrained tour. So this is Dubin's TSP. And there's also double integrator TSP, which has some acceleration to the TSP. And this acceleration is added through a double integrator. And this is rather close to control theory because double integrators implies continuous time as well as continuous space. And also in their paper, they present some probabilistic results. So I say this because their paper actually complements ours pretty well in the sense that they propose probabilistic results. We like to propose some deterministic results. And also they have some, as I just said, some continuous time, continuous space model, whereas we propose another model, this time discrete. So the model we propose is the racetrack constraints. So the racetrack constraints come from a little game, a paper and pencil game known pretty much all over the world, in which you have a little entity which has to do a tour to win the game. But we're interested in the constraints here. So it's round based. And so every round, your entity that you control or that a player controls is determined by a position in the plane, so X and Y, as well as a velocity vector, which can be seen over here at the bottom, which is represented by dx dy. And now every round, the player is allowed to modify the velocity vector by plus or minus 1 in every dimension. Or you can just stay at 0 if you like. So these are all the options that are proposed in the first round. Let's say we take this one, then the entity will move here. And now its velocity vector is defined as taking the difference between its current position and its last position, and then translating this obtained vector to your current position, which is what is done over here. And as you can see, this little model, this little discrete model, actually represents quite well acceleration forces, inertia forces. For example, this little entity has to spend at least maybe 5 or 6 rounds before it can turn effectively to the left, as you can see. So how do we define the vector TSP in which we add these racetrack constraints? We do this as follows. So as an input, we consider n cities in the plane, or not necessarily in the plane, but let's keep it simple for this presentation. So n cities in the plane with the starting city P0. So over here, that would be the little, the location of this small drone in the middle. And then the output would be a racetrack trajectory of minimum length, so of minimum rounds, if you prefer, visiting all cities starting and finishing at P0. So we like to represent such a racetrack trajectory as alternating red and blue vectors, as you can see over here. Now let's start with a little bit of insights in this new problem of vector TSP. Probably the most important insight that we present is the following. So we say that even if you are able to compute an optimal TSP visit order or Euclidean TSP visit order, then this may still not be enough to solve vector TSP. In other words, an optimal eTSP visit order may not be optimal for vector TSP. And we prove this through this little example. So you have how many nodes? You have 10 cities over here with starting city at the top over here. And you can see that if you force the visit order to be the Euclidean optimal visit order over here, then you obtain some result over here, but which is not optimal because over here you have a better result. So this is actually the optimal result for this little instance. And you actually do a little crossing like here in like an 8 formation. And this actually saves 2 vectors in this example. And it's a nice little corollary. This also shows that an optimal vector TSP trajectory may in fact self-intersect, which is the case over here. So in terms of complexity, vector TSP is complete. And so we do this based on a proof from Papadimitriou from 77, in which he proved that Euclidean TSP is NP complete. And so I'm not going to go into details, of course, this is a very non-trivial proof, but the main idea is to take an instance of exact set cover and then construct this zigzagging tour over here for vector TSP, which then goes to the starting city, and then put some islands of cities very far away from the zigzagging tour and very far away from each other, which are visited in some particular manner depending on the exact cover instance. So in the other way, so we just proved that vector TSP is NP complete, but we also give another reduction. So a natural reduction from vector TSP this time. And so we start with a little lemma, which shows that the amount of different configurations, so x, y, dx, dy, of a visiting entity can take is polynomially bounded. Or in other words, the configuration space is polynomially bounded. We use this little lemma to prove that in a very natural fashion, vector TSP reduces to group TSP. And in turn, this also means that vector TSP naturally reduces to asymmetric TSP as well as symmetric TSP. So let's look at some algorithms for vector TSP. So we had some trouble finding a suitable algorithm for vector TSP due to the main difficulty that vector TSP does not give edge costs, whereas most TSP algorithms are dependent on edge costs to work. But so we made a solution. So we actually used we adapted the 2-opt algorithm to use whole tour cost computations instead of only edge costs. And so what is the idea here? Well, you start with some initial tour in which you do some flips. So some flips in the visit order of some cities to visit. So for example, over here, you can see that some flip has occurred. And then we call an oracle to see if this tour is better. So using less vectors than this tour. If this is the case, then we keep the flip and we continue on like this until we find the local optimum. And so we use an oracle here for these cost computations. And for this oracle, we give an implementation as well. And so for this, we actually produce a very original multi-point A-star algorithm. So as a reminder, A-star is a search algorithm which goes to search through the configuration space given a fixed visit order. So the oracle gives a visit order. The oracle takes a visit order, sorry, and outputs some optimal cost. And so to guide this A-star algorithm, we had to develop a guiding heuristic, which is the following. So basically, we project the order in which the cities has to be visited on the x-axis as well as on the y-axis, and then we compute exact costs on these one-dimensional instances, and we return the maximum of these two. And we prove that this is a suitable guiding heuristic. In other words, it underestimates the real cost. So lastly, for this part, we did some experiments, and so we had mainly two aims for these experiments. First of all, we wanted to try out our algorithm that we implemented, so the 2-opt, using the A-star. And of course, we wanted to motivate this new problem of vector TSP as an independent problem, especially from Euclidean TSP. And so what we did is we tested if an optimal trajectory on the optimal TSP visit order can often be improved through our 2-opt heuristic. So in other words, we wanted to test if Euclidean TSP visit order is close to a local optimum. And so it turns out that, well, let's look at the results. It turns out that it's actually not always a very good local optimum. Indeed, in the first experiments in which we wanted to vary the number of cities, so we went up from 4 up to 12. In these experiments, we found out that, so at the end, for 12 cities, close to 50% of the instances tested found an improvement through a flip, starting from the optimal ETSP visit order. Next up, the size of the area. So we cannot really conclude any useful information from these tests. I suppose more tests should be done to conclude if the size of the area has a real impact on this problem, because it doesn't seem like it does from these tests at least. And then as a final experiment, we tried varying both of these parameters. So we varied the number of cities as well as the size of the area, but while keeping a constant density. And so you can see that even in this case, where you vary both parameters, you can see that at least 50% of 12 city instances can be improved through a flip. So quickly on this little conclusion for this part, we modulized speed, acceleration, and inertia in TSP through the racetrack constraints. We had some insights, as well as some complexity results and some reductions. And we adapted the two heuristic so that it could work for vector TSP using a multi-point A-star algorithm. And in the end, we did some experiments to motivate the problem. So as future work, you may be interested in implementing other heuristics. So I'm thinking about random insertion, because this would be a natural algorithm to try to solve vector TSP. Again, this one doesn't really need edge costs. It can work with whole tour computations. And you may be interested to prove that the problem is NP hard, but with unbounded maximum visiting speed, because our proof relied heavily on the fact that the maximum visiting speed is bounded and very small, by the way. Or you may be interested in proving that this problem is approximable, or maybe not. So this is not known either. So that's it for vector TSP. Let's now continue with the mobility models. So this can be seen as an intersection of these two big domains. So this part is based on work with Arnaud, and we recently published a little software package coded in Java using JBotSim, and we published this on GitHub, where it is free to use for anyone. So let's start with a bunch of definitions. So we define a manette, or a mobile ad hoc network, as a swarm of mobile agents with given mobility constraints. So these mobility constraints may be racetrack, for example. And then you say that the induced temporal graph of a given manette are the agents, which are then represented as vertices. And whenever these agents are close enough, so when they have some certain proximity, then they can create an edge of communication or interaction in the induced temporal graph. So a little example over here. If you have a manette like this, and these are the communication ranges of the entities, then the corresponding induced temporal graph would be this. And you can see that this is indeed a temporal graph, because over time, this entity will probably move in this direction and will cross paths with the third entity. And so a link will appear over here. And this one will surely disappear over time. Now, a mobility model can be defined as an algorithm controlling a manette in order to execute a given mission. So mission here in context of manettes are mainly defined as exploration or surveillance, stuff like this. But in this part, in this presentation, we consider a mission to be the fact that we can ensure that the temporal property is present in the induced temporal graph. So what I mean with this is, when you look at all of the possible temporal properties that you can have in a temporal graph. So by the way, this is a hierarchy of temporal graph properties, which was introduced in CASTEIGTS et al. In 2012. So these are all temporal properties which you can have in your temporal graph. And for example, we have here temporal connectivity, which we talked about at the beginning of this presentation. And if you look at this temporal property, for example, this is actually the class of temporal cliques. So we already saw some of these properties. And these are actually useful to have in your temporal graph because these can represent necessary or sufficient conditions for some certain algorithms to run on your manette or on your temporal graph. So I prepared a little example. So for example, if you have this mobility, which induces KR property, then you know that leader election will actually succeed by eliminating whenever two leaders meet, one of them is eliminated. And so this simple algorithm, distributed algorithm, works in the case when you have the property of KR in your manette. So which is the case over here. However, this simple algorithm, where leaders eliminate one another, does not work, for example, or may not work in a temporal graph where only PR is ensured. So as you can see here, there seems to be 3 leaders because there's there seems to be 3 swarms of entities over here. And since they do not meet, they cannot elect a leader amongst themselves. Now, how do we start with, so as a reminder, we would like to create mobility models that ensure a given temporal property on the induced temporal graph, okay? And so given some manette with some mobility constraints. So that's a lot of things to take into consideration. And so we actually thought up a little plan to maybe make it a bit more simple. So we introduce atomic mobility models, which are mobility models, very basic and simple mobility models for a mobile agent. So not for a whole manette, but for a mobile agent, which we then use to construct mobility models. And these atomic mobility models are actually very basic. So they are basic enough so as to be independent of the mobility constraints. Or in other words, we assume that any possible mobility constraints can at least accomplish these simple tasks. So what are these simple tasks, you may ask? Well, there's messenger, which is just the mobility model, which makes you go to a given destination. So this is solely parameterized by a given destination. There's roundabout, which is parameterized by a center and a radius. And so a mobile agent will just move around in some circle around this center. And as a last atomic mobility model, we propose the swarm mobility model, which again is parameterized by a center and a radius. And now the mobile agent can actually move in a random fashion inside of this swarm. So these are the 3 atomic mobility models which we use to construct mobility models for manette. So let's quickly go over these proposed mobility models for manette. So we propose the swarm mobility model for manette. So there's actually a lot of properties which can be ensured through this swarm mobility model. I'll just show one. So this is CR. So CR is the property of the induced temporal graph possibly being connected at some snapshots, and this recurrently over time. So as you can see, there's one messenger which goes back and forth, and the swarms are positioned just right so as to possibly create a connected snapshot over time, or recurrently over time. So next up is the grid swarm mobility model, which functions in the same way as the swarm mobility model, except now you have an underlying structure which ensures that the graph is always connected at any point in time. The temporal graph is connected, and so connected in the static sense of static graphs. Next up, the 3rd one is the token mobility model, which starts with one node having the token and transferring it to a neighbor whenever it is close enough. And only the node with the token can move. And so this induces the property of periodic edges. So whenever this token passes through the whole manette and comes back, then the edge that appears is actually periodic in appearance. And lastly, we have the roundabout mobility model, which does the following. So it's similar to the token mobility model, but now instead of giving the token, well, it keeps it and it just says to a neighbor whenever it crosses it, okay, you can start moving now. And so you may think there's some lag in this video, but actually there's not. This is done on purpose. So at some global time, the manette will decide to maybe move slower altogether or move faster. And so this ensures the property of EB, which is the reappearance of edges in a bounded time window. Now let's quickly go over the mobility constraints. So as I talked about before, any mobility, we assume that any mobility constraints can do at least the 3 proposed atomic mobility models. So we only implemented 2 mobility constraints, being racetrack, so the one we talked about before, as well as a very simple mobility model named grid walk, or which we name grid walk, which is just a random walk on the grid, or well, not maybe random if we organize it in a certain fashion. And so these two mobility constraints are all implemented for these proposed mobility models. And so, do I have some time left? I think so. Maybe I can just end on a, okay, and maybe I can just end on a quick note on a comparison between these two. So even though these execute the same mobility model, so in essence, this is the same mobility model as the following video I will show you. You can see that there's a large, well, there's a certain difference depending on the mobility constraints. So this is a mobility model with two swarms in which there's one messenger which goes around from one swarm to the other. So this is the same mobility model, but this time with grid walk. And you can see that even though they execute exactly the same mobility model, there's a slight difference in aesthetic appearance. So as a mini conclusion for mobility models, we implemented some mobility models ensuring some desired property or excluding some desired property on the induced temporal graph. And so these are independent of the mobility constraints thanks to the proposed atomic mobility models. So as a future work, you may think of customizing a bit more your manette, because at the moment, the number of agents and the area that they cover are all fixed. So we may continue in this direction to give users the possibility to customize the manette. Or we may continue implementing properties. So there's two properties that we saw before, which we did not implement. And also there's some new properties being proposed in the literature recently. And so we may implement these in the future. Of course, we can also implement some other mobility constraints because all we have to do is implement these for the atomic mobility models. And so you may think about double integrator or the Gibbons vehicle. Now, as a conclusion, as a whole, on my thesis, we did some interesting work in mainly two domains, so temporal graph theory and motion planning. And we also wanted to look into the intersection between these two. And so I think we did a good job on these three subjects. And so maybe to conclude, so should be quick, but maybe to conclude, I had a nice time working on temporal graph theory. And so I hope to continue to work in this direction in the future, maybe as a postdoc. Thank you very much for your attention. Nicolas is coming.
Yes. So now it's time for a question. So Paola will start.
Thank you for the very nice presentation. It's very clear. I also enjoyed reading the text.
Just a second.
Yes.
Yes, Paola, can you try to talk?
Can you hear me?
Yes, we can hear you.
So can I go ahead?
Yes, go ahead, please. We can hear you fine.
I can hear an echo. I hear myself.
Oh, okay. That's maybe my own microphone.
Maybe I have to move mine. Okay, I'll try again. It's a bit weird.
Okay.
Paola, you can speak. I will mute Jason.
Okay, let's see if it works now. Yeah, I don't hear myself anymore. So I was saying that I really liked your presentation. Was very well done, and I enjoy reading your thesis. I like your results, especially the ones in chapter 3, because maybe that's the closest to my interest. So my questions will be mostly focused on your chapter 3. Okay, so I appreciate the difficulty of the problem. It's not easy finding sparse spanners. And can you give an intuition of why it's so complicated to consider more general graphs? Now you look at clicks, it might seem such a big restriction. Of course, I understand, but you don't really explain, you don't elaborate on the difficulty of the problem. Can you say a few words about that? I'm muting myself now.
Okay, so I should be unmuted. So yes, so to answer your question, so why is it so difficult to construct maybe sparse spanners in other classes of temporal graphs? Well, I think maybe, so let me just think a second about this. Well, maybe it's not that difficult if you pick your class, if you pick a correct class. So, well, CLICS was of course very difficult, but maybe it would have been easier to consider, I don't know, other dense graphs like complete bipartite graphs. Maybe this question has not yet been studied, and maybe it would be easier to find sparse spanners in these classes. But then again, maybe not. I didn't really look into this subject. So what can I say else? So our results actually are very adapted to the fact that this is a temporal clique. So I think that even the fireworks techniques would not be able to work on any graph outside of the cliques. Well, maybe some graphs that resemble cliques, like maybe dumbbell graphs or something like this would work. So maybe it would be easy in these types of graphs, but in general, so as I've shown before, or as I talked about before, when Axiotis and Fotakis gave a counterexample, they had a bit more room to work in maybe, and so that's why they were able to find a counterexample. So maybe if you restrain your graph classes a bit more, then you cannot find, then you have not enough room to maybe find a counterexample.
So you mute again yourself and I talk. We continue that way, or let's see. Okay. You mentioned a few times that your techniques, by the way, very nice techniques you're using in this chapter, may have a wider applicability. And I believe so, I agree. You just mentioned that some of them are really specific for the clique, but what type of wider applicability can you envision for different problems or for the same problem in other settings? What do you think?
So very good question. Well, personally, when I went to visit our co-author, so Joseph Peters in Vancouver in Canada, we tried to see what could be done as a bit of an extension of this work. And so I think your question is a bit like this. And so we went to look at the other, so maybe I still have this over here. Yeah, so all of these other temporal properties, we wanted to see if there were temporal spanners, for example, which were easy to obtain for other temporal properties. So we talked about temporal spanners, which ensure temporal connectivity, right? And so maybe it's easier or harder, I don't know, to consider some other temporal properties. And so we had some first results on all of these other temporal properties over here, which worked out pretty well. Some of them used actually results that we had from here, or techniques that we had from over here.
Okay, so some of your techniques you already have in mind how to exploit them in other classes. Okay, and just one clarification about your assumptions on the labeling. So you're saying that the locally exclusive single labels that you use for strict journeys, so this is not really a restriction, or is it partially a restriction? Because in two parts of the thesis, I can read it in a different way.
Yeah, so this question is actually asked a lot whenever I present this subject. So why are we able to consider single, locally unique labels like this? Well, we have a little section in the paper, of course, which talks about this. But so the main idea is that most of the temporal cliques can reduce to an instance of only one label, locally unique label, by the way, except for one specific case, which I did not talk about here in the presentation. But so there's one specific case which may not be, or which induces another problem, which is actually very hard to solve, to obtain locally unique single labels. So in conclusion, most of the cases can actually be reduced to this simple labeling. And there's only one specific case which may not be able to reduce to this case.
Oh, I see. So most except for one specific case. What is this one case?
Oh, so I think so. You would have to look at strict journeys and non-strict journeys. So there's a distinction between these two. And I think when you consider strict journeys and you have a lot of locally, so if you have strict journeys in which there's a lot of labels which have the same or a lot of edges adjacent to a single vertex with the same labelings, then you may have a problem.
Well, of course, we have the pathological case where every label is the same.
Yes. And so in that case, if when every label, so the whole graph has the same labels on every edge, in that case, if you consider strict journeys, then the problem is not solvable.
Yeah, but apart from the pathological, so your choice of limiting yourself to single labels that are locally distinct is necessary in a sense, or not really? I mean, except for the pathological case. Let's forget about that one. Is that a restriction or not? Or
so I think we mainly did this these single labels because it was easier to work with. I don't think it's really necessary to work on single labels. You may just work on your input graph as a whole without reducing it to single labels. But I think it's just easier to work with, and our results are already quite complex as is, and so maybe it's just a better way to present our results.
okay, another question. Okay, your last chapter, now in your presentation, you did show beautiful, nice examples like the leader election and so on, and it makes a lot more sense. By reading the chapter, there was a section on examples where really, I mean, you only mentioned very briefly leader election, green nodes, red nodes, but nothing was there. So I found it a little bit difficult to read that one, but now of course with the example everything makes sense. But maybe you may want to, I don't know, maybe add some pictures or some little description so that it makes so that it's more complete. Now my last question is still a little bit about open problems in a sense, connected to the previous one. I have the feeling that you have a sense that your open problem on the existence of linear spanners in arbitrary, in cliques is, you think it is true? You think it is possibly to prove it? I mean, your feeling is more on the positive than on the negative. Is it so?
Yes, so if you're asking if personally, I think that we can always find linearly sized temporal spanners in any given temporal clique. I don't know, actually. At first I was convinced because Arnaud did very extensive tests on this question, and we always found the same results. So either there's a spanner of a minimum size spanner of size 2n-3 or 2n-4. So by brute forcing our way through examples, we actually always found the same answer. And so maybe there's some hidden structure which has yet to be discovered in this. And so I think we did talk about this in the paper as well as in my thesis, but I'm not sure if we can state it as a conjecture, because maybe there's not enough data to state it as a conjecture.
Okay, thank you. I'm done with my round of questions. Thanks.
Thank you, Paola. So now Rolf will have to ask a few questions to Jason. So can we hear you? Sorry, Rolf?
Yes.
Okay.
So I'm ready. Sorry.
We can hear you.
Okay, thank you. So maybe I start also with the chapter number 3, your first problem. So thanks for the very nice talk, actually spanning graph theory with very applied stuff. It's rare and it's very interesting and entertaining in a way. So if someone would ask you to specify a clique in practice, would you run, what kind of algorithm would you run based on your methods?
Sorry, did you ask if someone asked me how to
practically specify a clique, so to say, in this setting? would you say, okay, in practice, you rather should do it a bit differently, or would you do it right like this?
So I think the method presented, okay, can you hear me? Yes. So the method presented in my slides were the proof for the n log n sparse spanner, but maybe you can actually try something else. So we also presented two techniques, which in general don't work, but in most cases they actually work pretty well. So if you give me any temporal clique, then maybe I can try to use, yeah, there it is. Either dismountability, so try to find a vertex which can always be removed in a recursive fashion. And then you can actually find a very nice minimum size temporal spanner. But this does not always work for any temporal clique, but I think it works just fine in general case. Also, there's another technique which we call pivotability, which is over here, in which we use somewhat of an analog of Kosaraju's principle for directed graphs. So we search for a vertex which can receive messages from everyone in the graph, and then distribute all of these messages into the graph after some given time point. And so this again does not work for all cliques, but I think it's a very good technique to try on any given clique to see if it works or not. And then in the end, if all of this fails, then you may try to apply the fireworks technique, of course.
Thank you. So did I understand correctly? So your methods really directly apply to cliques, but even to quasi-cliques or very cliquish graphs, you're lost already? Or how robust is your method?
I think, yeah, I think from the point on where you don't have, let me think about this. So at some point in our algorithm, we say, yeah, so it's not over here, but at some point in our algorithm, we say that, so it's at case one. In case one, we say, okay, we dismount the vertex and we repeat. And so this is actually not possible to assume that you can dismount a vertex in case one if you're not given a temporal clique to start with. So it would not, so our algorithm would probably not work starting from there.
Okay, so thank you. So since Paola took quite some questions here, maybe I move to vector TSP a bit, if you like. So you started off with saying that people in control theory look at it, but you look at it from a discrete point of view. You discretize. So could you compare these two worlds? In what sense? What would be the advantage of discretization compared to what they are doing, or why is it also motivated, better motivated, different motivation?
So I think that the discrete way to present the problem may be more prone to algorithmic investigation, whereas the discrete version of the problem with the double integrator and the control theory relies maybe more on some analysis of continuous functions, for example. So it's really quite different, I suppose, to compare these two versions, although they share many properties. So I don't know. So what was your question? What is the main differences between these two problems?
Yeah, or what makes them very different in nature? I'm not very familiar with control theory. That's why I want to understand if you have deeper insights, what's going on there. Okay,
so I think to answer your question, they're not very different at all, except that we look at them in a different way. So either algorithmic or either analysis of continuous functions. Mm-hmm. So I don't for an outsider whenever they look at the results or maybe the problem. But for the people working on them, they just have a different vision, I suppose, of how these things should be treated.
Okay, maybe a very speculative question. So I could imagine that you could also define something like, I don't know, tourist or sustainable TSP, where you have some upper bound on speed and a lower bound on speed, but if possible, you want to continue in almost the same speed all the time, because this is very efficient if you don't accelerate, and it's very cozy for tourists sitting in the bus or whatever. So could you solve such a or take such a problem with your approach as well? Or?
So I think that if you fix some given maximum speed, then you can somewhat solve your problem. So if your cities to visit are very far away from each other and the maximum speed is very small with regards to the distances between cities, then maybe your problem can very well be approximated by Euclidean TSP. Because all you have to do is consider that you start or you accelerate to your maximum speed, then you continue on. Speed, maybe this takes some time, and then you just put an edge between these cities which has a cost about the time taken to cross this distance. So I think it would be it would be close to Euclidean TSP.
Okay, thank you. So one more question here. If you assume your points are in the plane, and so if all cities or points would be in convex position, so they are all on the convex hull, then your problem is trivial, no? Vector TSP?
So I wouldn't go as far as say that it's trivial, because so I think you already asked this question when I presented in Berlin.
Sorry.
So which is over here. And so we talked about a little fact before in vector TSP, where I said that an optimal eTSP visit order may not be optimal for vector TSP. And so I put another version of this fact in over here. And so it turns out that as a corollary, points on a convex hull, such as over here, do not necessarily admit the trivial visit order. So the trivial visit order being the visit around the convex hull as an optimal visit order. So does this answer your question?
Yes, thank you.
So of course, this relies quite heavily on bounding the maximum visiting speed. I think this also works for maximum visiting speed being 1, because you just remove this and this vector. But it does serve as a counterexample in the general case.
Okay, thank you. Maybe one more question. You know that I'm from a parameterized complexity world as well, and so you showed this very complicated NP hardness result. It's quite based on this previous Papadimitriou result. So if you want to do some positive results in terms of parameterized algorithms, fixed parameter tractability, what could be reasonable small parameters to choose for vector TSP, and which gives hope to get something tractable if they are small?
So I don't have much experience in fixed parameter tractability, but maybe to answer your question, in our problem, in the paper version, as well in the thesis, we actually add an additional parameter which represents the maximum distance between cities to the problem. And so maybe if you remove this extra parameter from the problem, then you can say, maybe, I'm really not sure, but maybe this parameter would be interesting to look at in terms of fixed parameter tractability. But again, I'm not really sure. I don't have too much experience in this area, but I would like to.
Maybe one just simple follow. I don't even know whether it's in your chapter. So, but if you assume you only have 2 speed levels, for instance, only 2, is it already hard, your problem?
So do you mean with 2 speed levels? So maybe speed 1 and speed 2, something like this?
Yes, please.
Is it already? So your question is it already NP hard? I suppose so. I suppose it is, yes, because I think our proof from Papadimitriou still applies in the case where you only have 2 speeds. But again, I'm not too sure, but I think it does apply. So it's a bit further away. Just a second, sorry. So it's over here, and so this proof works in the case of if you want to reduce exact cover to Euclidean TSP. And so maybe if you consider Euclidean TSP to be at fixed speed, so speed 1, then you still obtain the same reduction, proving that Euclidean TSP is NP hard. So maybe having your vector TSP at only 1 speed or maybe even 2 speeds would still be NP hard due to the same reduction.
Okay, thank you. I think I used up my time. Thank you very much. Thank you.
Thank you.
Thank you, Rolf. So now, Eric, it's your turn.
Yes. Do you hear me?
Yes, we can hear you.
Okay. Well, first I will be also, I'm very happy with the defense and your presentation, which really completes the manuscript. And Paola and Rolf already asked for very interesting questions, but hopefully they left a few for me. One of the first questions would be, well, you present at the beginning of your text the classification, and the classification for the static graphs is based very often on different structures that may be present. And when I speak about structures, I mean subgraphs. But then when you present the classification that is already in the literature about temporal graphs, it is really oriented toward connectivity properties and often...
I'm sorry, Eric, could you
Yes?
talk a little louder, because I don't really hear half of the sentence.
It's not loud enough.
No, sorry.
Okay. I will just verify my microphone. Okay.
So maybe if you just talk a little louder, then it would be okay. But it was just on the border of not being hearable.
Okay. Is it better now? Is it better that way?
It's better, yes.
Okay. I will keep speaking at this level. Yeah. So maybe I was asking myself, could you elaborate on maybe classification on a temporal graph that would use some structural properties? Well, about as I said, about subgraphs. Do you think this would be possible for temporal graphs? And the other half of my question is, then maybe can you use this classification and apply it to the Spanner's findings?
Okay, so let me just answer the first question. So your question is basically, can we maybe be interested in another classification? So where is it, the classification? No. So considering this classification, even though mainly this hierarchy is heavily based on temporal connectivity, there's still some classes which represent structural properties, I suppose, because, for example, this one, being the class of temporal cliques, implies that your footprint, your footprint is complete. Maybe there's another one. Yeah, maybe. Yeah, of course, this one, because it's a generalized version. But to answer your question, could we create a hierarchy of structural properties? Yes, probably. I mean, why not? We already have some hierarchies resolving static graphs. So maybe these can just be generalized as temporal graphs. So why not? So do you mean as in terms of the footprint? of the temporal graphs, or more generally speaking?
More generally speaking, yes. If we
course.
can find find it. And the other half of my question is, can you be more maybe? Do you think there might be some classes, some temporal graph classes based on structural properties for which you may find some interesting results about sparse spanners?
So I think, so maybe I can talk about one other research direction which you could take considering temporal spanners, which is that maybe you can, so instead of asking if there exists a temporal spanner or sparse temporal spanner, maybe you can ask, well, does there exist one which has a footprint which resembles a tree? So that may be another question, or do you have one whose footprint resembles maybe some other graph? So this may be another question which you can ask in terms of underlying structure of temporal spanners, which I think is a very natural question to ask. But I personally did not really go into this direction. So it might be interesting to indeed try to answer these questions.
Okay, and I've got another question that you discussed with Paola already a bit about this. It's about the techniques you used, and you said it might be difficult to adapt it if the graph is not a clique. But I wonder, and you said it afterwards about the pivot technique, and I think also maybe on the fireworks. I don't know. I don't think that it should. Well, I do not see why it would not be applicable to other graphs, which may not be cliques.
Okay, so let's go back to case one of the first subject, so which is over here. So did I unmute myself? Yes, okay. So over here in case one, what we do is we dismount a vertex and we obtain another temporal clique, which is why we are allowed to recurse on the fireworks technique. And actually, if this only works because, let's see, just a second. Yeah, so over here, you need to select some edges which allow you to transfer any messages, say you can have for everyone in the graph to some other person. So I suppose in this example, maybe you would need to keep this edge with label 3, as well as maybe this edge with label 14, and then you can dismount the vertex while keeping in mind these two edges, so that afterwards you can put back these edges in the final temporal spanner. And so I'm hesitating right now. Maybe this is applicable in a case where the graph is not a clique, which is contradicting what I said before. But yeah, no. Right now, I don't remember exactly why the graph has to be a temporal clique exactly. So
okay.
No,
thank you to admit it's not as trivial as it seems.
Yeah, so maybe it's before, maybe it's regarding the. Oh, okay. So maybe it's over here. Let's look at this. So maybe it's over here. So whenever you get a journey like this, you end up in some vertex. And so at this vertex, you select all of these edges. And since it's a clique, you know that all edges here, if you select them, well, they will reach all other. And I think this is the case where if you don't have a clique, for example, if you don't have edge 7 over here, as well as edge 8, then maybe your graph is not temporally connected by selecting all of the edges if there are some missing. So I think it's rather over here. Okay.
Okay, yes. Yeah. This is more convincing. Yeah, thank you. Well, I think there might be other questions about spanners, but I will go to the next chapter. about the complexity of VTSP. The proof you presented is really difficult to follow. It's based upon the proof by Papadimitriou et al. For the Euclidean TSP. So, of course, the natural question is, why wasn't it easier to make a proof, to transform the problem into Euclidean, a special case of Euclidean TSP to prove NP completeness?
So indeed, we had this question with Arnaud and with Mathieu. We asked this question a lot, and sometimes we had special meetings together for half of the day where we tried to find such a proof. But we always had something missing or something going wrong. For example, so you talked about the Euclidean TSP, maybe. So yes, you would like to reduce Euclidean TSP to vector TSP, which would be maybe a bit more natural, if I understand correctly. And so yeah. I agree with this, and Arnaud agrees with this, and Mathieu agrees with this. But, well, we try to do this, and so maybe one thing which can already create problems is that in Euclidean TSP, you consider real numbers. And so this already gives a first problem, but maybe this problem can be solved in some manner. But then you still have the problem that, yeah, so the problem is maybe that, you're working with vectors in vector TSP. And so these vectors can cross enormous distances if they have enough time to accelerate these distances. And so maybe that's why if you have some faraway points in Euclidean TSP, if you would like to reduce it to vector TSP, then you will need to put them really far away so as to maybe keep again some large distance or some large costs on this pair of points. But so we also thought about Dubin's TSP. So I talked a little bit about Dubin's TSP, I think. And at some point, we actually thought we had a nice little reduction from Dubin's TSP to vector TSP. But there was just one little technical detail missing, which made the whole proof which made the whole proof false. So in the end, we went with Papadimitriou. So I think we already had this proof maybe in the middle of our research. And we were not really satisfied with it. As you said, maybe Euclidean TSP would be able to reduce to vector TSP, or maybe Dubin's TSP, as I just said. So we still continued searching for other reductions, even though we already had one over here. And so how should I conclude on this question? Well, I don't think personally I will continue to search for a reduction like this. I think we spent enough time on it, but maybe there exists one which we just didn't find.
Okay, my second question of this chapter was precisely about the Dubin's model. So you answered more or less. What I understood better when with your presentation is that, in fact, Dubin TSP may be considered as a continuous version, or can you consider a discrete version of Dubin?
Yes, so Dubin's TSP is indeed discrete. No, sorry, continuous in nature, because you have to do some. You may be able to do some trajectory which has a curvature, and so that already makes it continuous in nature. So what was your question? Did you ask if that was the main issue?
Yeah.
So I don't think that was the main issue when trying to reduce Dubin's TSP to vector TSP. Actually, we were missing some upper bound between Euclidean TSP. No, so we were missing some upper bound which was trivial for Dubin's TSP, and so when we tried to adapt some other proof concerning Dubin's TSP, we actually missed out on this detail, which is crucial, but which was so trivial that it wasn't mentioned. And so we found out about it later. which made the proof infeasible.
Okay, thank you.
Thank you.
Just a last question about this chapter, about your version of A star. So you called it multi-point A star.
Yes.
You come up with a very high complexity to apply it. And so I was wondering, do you think you can do better, maybe with another kind of algorithm, or it's hopeless?
So just to be clear, are you talking about the oracle, which tries to output? Okay.
Exactly, the oracle.
So maybe instead of doing a general search of the configuration space, which we do with the multi-point A star, maybe you can try to find some specific structure which is hidden inside of this configuration space, which may allow you to obtain a better complexity or a better algorithm for the oracle. So at one point we tried a dynamic algorithm, but this didn't work out due to, again, a small detail which we found out in the end. So, but at some point we had a dynamic algorithm which worked fine on most instances, and it was very fast also. But for some instances it didn't work, and we actually found out that it's due to one little missing detail which sadly made the whole algorithm false. But maybe we can try to solve this little detail in the future.
Okay, thank you. Okay, this was my last question, Mr. President.
Ready?
Can I? So I'm next, right?
Yes, go ahead, Quentin.
Okay. Okay. I hope there is not too much sound around me, because there are some works around, but fully it will be okay with me. Okay, perfect. So first, yeah, thank you for the nice presentation, and for the document, for the thesis. It was really nice to read, and really interesting, and so yeah, I learned a lot of things, and I think it was really easy to follow. The beginning, you talk about maybe it's something that maybe looks easy at first, but it's really important to start with all the basics in order to present the meaning. So it was really nice to follow. So my first question is about, actually, I will come back to almost the same question as Paola about the first problem you mentioned, because you presented me the problem 3 years ago when I went into Bordeaux, and since then I remember this problem, and actually I spent some time trying to prove the conjecture, and I failed so several times actually. So I was hoping you gave some insight about how to prove, and what was your opinion about that, but you already answered that. But so my question is more like, you made some. You dismount some nodes, you make some, you compute the fireworks, and in order to have the bipartite graphs. And I was wondering, in this process, if you lose something or not. For instance, like if you prove, like in the bipartite graph, that you cannot have a linear number of edges, does it mean that in the complete graph there is no linear size spanner, for instance?
Okay, so this is actually a nice question, and we asked this question to in the context of a little internship for a student which we had, and he tried to answer. Well, we gave him the problem, and he wanted to try to answer this exact problem or this question that you asked. So in other words, does the complete bipartite graph, so case 2, does it imply a local optimum? So this is maybe your question, and I think so. The internship turned out. So we thought that actually we had a little result, which turned out to be false. But I think we learned a lot during the internship. But so maybe to answer your question, I think yes. I think yes, that whenever we get to case 2, I think there's bound to be maybe some structure that we lost along the way, and so maybe there was a linear sized spanner in the temporal clique, but we just lost it because we ended up in case 2, and I'm pretty sure that this may definitely be the case. But then again, I don't have a formal proof. This is just intuition talking.
So you think you can lost something, or you
Well,
can't?
yes. So as a conclusion, I think you can actually lose getting a temporal spanner of linear size, for example.
Okay.
And
So I was wondering as well, did you make some experiment just on the second case of the bipartite graph to see if you always come up with a linear size solution just for the bipartite graph?
So I personally did not do any experiments, but I think whatever I just said, because whenever you get to case 2, you already removed essentially half of your original edges. And so there's maybe a high chance that one of these edges, of half of these edges, was very important to maybe keep for a linear size spanner. So I think, so that's why I said that it's very probably that there's something that gets lost along the way. But I didn't do any experiments, no. Maybe Arnaud did some. Knowing him, he probably did some. So maybe, I'll ask him later. Okay. So my intuition says yes, but I don't have any experiments or even proof to show this.
Thanks, perfect. Okay. So now on the vector TSP, I also had a question that was kind of answered in one slide that you showed. It was, I was wondering if you take the Euclidean TSP, and if you take the visiting speed to 0, if you can, if the solution for the Euclidean TSP can be converted into a solution to vector TSP, and you showed the slide that you can still find solution instance where it's not the case, I think. But I was wondering if in all your experiments you shown where you take for an instance of the Euclidean TSP, a solution of the Euclidean TSP, and you see if it's a local minimum. In all your experiments, you show that there is a high ratio where it's not a local minimum, right? And I was wondering if you already also made this kind of experiment with a visiting speed of 0, and if it's also like a very common to have an optimal solution for the Euclidean TSP that is not a local minimum for vector TSP when the visiting speed is 0, or is it really rare or something like this? Or... No. Yeah.
So to repeat your question, I think you first asked if considering vector TSP with 0 maximum visiting speed, if it reduces or if it becomes another TSP, and I think it does, because all you have to do now is search for a shortest path between any 2 vertices, and you can just draw some edges and put on these edges the cost between these 2 pairs of vertices. So indeed, if you consider 0 visiting speed, so if you have to stop on every city, then I think it becomes probably a symmetric TSP, and maybe even you get maybe even be able to show that there's the triangle inequality in this TSP. So you may obtain maybe a metric TSP, which can be solved.
Yeah, but when Rolf asked the question earlier, you showed slides saying that even for v equal to 0, you have some property and so I thought it was written that something that contradicts what you say, but yeah, an optimal ETSP order may not be optimal for VTSP. So that means that you cannot. So that means that if you take a route and you from the optimal ETSP, and it's not and you take the optimal trajectory along this route.
Okay.
It may not be a local minimum, or is it? Or is it because?
Are Are you asking about this result or this, this
actually,
trajectory over here?
I don't exactly know about the figure, but just about the fact that it's written above, like if you take a visit order from the optimal, that is a solution for the which is optimal for the ETSP, and you compute the trajectory using a race trace, is it an optimal solution for the VTSP or not? Because,
Oh, okay. So that is actually this fact. So indeed, if
with V equals 0.
Yeah. So even with V with nu equals zero. So if you have to stop on every city, then the Euclidean TSP visit order would trivially be this one, or shown at the top over here. And so I don't remember how many vectors you would need or how many rounds you would need for this one, but it's actually 2 more than this visit order. So I think that answers your question. So even if you bound your maximum visiting speed to 0, so the minimum, then Euclidean TSP is still not, may still not be an optimal solution.
Okay, so I understand.
Yes, and so the intuition comes from the fact that you can just accelerate quite heavily whenever you go from the last point to the first point back again. And this uses, I don't know how many, 8 configurations or 8 vectors, whereas over here you already almost use 8 vectors to reach one point in the middle. You see?
Okay. Yeah.
So that's the main idea behind this.
Okay. And so so the follow-up question was in your experiment when you try to compare the solution obtained from ETSP and you see if it was a local minimum or not. You saw that the ratio, a lot of them were actually not a local minimum when the number of nodes was large. And the question is, what happened to this graph if you consider a maximal visiting speed of 0?
So your question is, what would happen with these experiments, or rather with the results of these experiments?
Yeah, the results, yeah.
If you bound the visiting speed. Good question. So what would happen here? So I still think, of course, that there may be some flips because we may have the example as I shown below. So even with a bounded visiting speed, you can still flip your Euclidean TSP to obtain a better one. But maybe, so again, this is my intuition speaking, but maybe it would not be as easy to obtain a better visit order as you would with unbounded visiting speed. So as we consider here, so maybe you would see a small rise, but not as much as you can see over here. So not as much as 50%.
Okay, thank you. So I don't know if I have time for the question. But, Nicolas, okay, so I continue a little bit. Maybe one more. So about I come back to the first two, but yes, I can. Okay. So I come back to one chapter before, and I was wondering about like if you saw problems where having a sparse spanner, temporal spanner was useful or not. Like, what are the application of this having a sparse spanner? Did you saw example in the literature where it could be used to solve other problems or not? I was just wondering.
So I think in practice, what you would do if you have a network, so a temporal network, if you have one of these and you would like to obtain, or you would like to remove some connections which aren't necessary, I think in practice it would be better to just recreate your network so as to minimize the number of connections needed. So that would be possible only, of course, if you can just shut down the network for maybe the time needed to create a new one. So maybe our result for temporal spanners would be applied more in the sense that if you have a network which cannot be shut down, which has to run indefinitely at any point in time, then you may try to compute the temporal spanner on this network without shutting it down. And so that may be an application for temporal spanners. But I think, so as I said, in practice, maybe you would like to shut down the whole network and just create a new one.
Okay,
and I don't see any other applications right now for temporal spanners other than that.
So maybe just now last question. I was wondering if you looked into online algorithm for, or the online version of the problem finding sparse.
So here you're talking about temporal clicks, right? Temporal spanners?
Still this problem.
So the online version would be if you add over time some more vertices, which are all connected to the current graph, would you be able to obtain a sparse temporal spanner? Is that somewhat your question?
Yeah, if you maybe it will be, yeah, the problem would be really different, but like, yeah, if you don't know the whole future, and you have to take the decision of which edge you have to keep. So maybe this is I don't know if you looked into it or not.
Yeah, so maybe you would be able to create some kind of a database which every vertex has access to, and in that sense, every vertex is aware of whatever happens in the graph. And so maybe in that sense, if you construct a database from the ground up, in which nodes come and or rather connections come and go, maybe in that sense you would be able to say, well, okay, the following connection is actually not needed, so it can be removed if that's what you're thinking about. So maybe this would be possible, but I suppose you would have to have some common database in which every node has access, but I'm not really sure.
Okay, so thank you again, Jason. I left.
Thank you.
Thank you, Nicolas.
Yeah. I will ask my questions from here. So first of all, thank you very much for the nice presentation, also for the nice manuscript. Well, I have two small questions, hopefully. I don't want to make this too long. The first one is, when you look at temporal spanners, so what you did, you took a complete graph, and for that complete graph, you gave a procedure on how to throw out edges to make it sparse. There's also this other approach where you have an input graph given, and then you have a procedure that does this. Have you looked at this at all?
So are you talking about you're given, say, a static graph, and then it's up to you to put the labels on these edges?
No. You've given a static graph.
Yes.
With the labels, and you have an automatic procedure that does this. So you don't have a specific procedure for one graph, but a generic graph with labels, and then you try to see, and the goal is to compute the one which minimizes, and then can you approximate this problem? You have not looked at this?
I'm not sure if I understand the problem correctly. So you're given an input temporal graph with labels on the edges,
yes.
and
which is
temporally connected, okay.
Which is temporally connected, and then you have an automatic procedure that produces the minimum number of edges, so throws out the edges. Whereas here you do it by hand, sort of, for one specific.
So here, yeah. So here at oh yeah, sorry. So our algorithm does. I would consider it automatic already, but maybe you mean, how can I say this? So maybe you would mean, instead of procedurally removing edges, you would like to remove all of the edges at once?
No, instead of starting with the complete graph, would, for example, the steps you take, would they do something for a generic graph that you like? Put a grid, would your algorithm, your steps also be able to do something for a grid, for example?
Oh, okay. So, in other words, does our algorithm generalize? Is our algorithm applicable to other graphs?
Yeah.
Oh, okay. Let's say that. So, so as I stated before, at some point in the algorithm, it heavily depends on the fact that your given input graph is complete. Okay, and so if this is not the case, then at this step it would already not work. But so, as I maybe talked about before, maybe you can actually consider click-like graphs, such as maybe, so I talked about dumbbells, I think, which are two clicks, which are connected by some edges. So maybe this would still work. Maybe the procedure can be adapted for complete bipartite graphs. I'm not sure.
And the other question, okay, there's other questions here, but they all have been asked before. So the other question is, you mentioned for the vector TSP, it would be useful to have to think about approximability. So for example, if I understand it well, your algorithm, is it a true approximation, a constant approximation? Is it not? And do you have any ideas for algorithms that would be, or is the problem too hard? How hard is the problem?
Yes, so this is a good question, because even though our algorithm is based on a heuristic named 2-opt, it is actually not a 2 approximation. The 2-opt is, yeah, the 2-opt reflects something else. It means that you switch 2 pairs of vertices. So this has nothing to do with approximation, but maybe to go into the question of approximation, at some point we talk about how our graph, so do I have it here? It should be around here. So over here, I talk about the fact that vector TSP naturally reduces to group TSP, which in turn reduces to asymmetric TSP and symmetric TSP. And so these TSPs are actually known to be approximable if you have the triangle inequality present in your graphs. And so our reduction actually does not return a TSP with a triangle inequality. And so I think maybe as a future work, we can look again at this reduction and maybe try to see if we're allowed to visit a vertex multiple times, because if you're allowed to visit a vertex multiple times in a TSP, then you can assume that's the same thing as saying that there's a triangle inequality. So it's basically the same thing. And so we're going to look at this if this is possible, because if it's possible, then we can assume that maybe vector TSP is approximable.
Yeah, so just one thought. So what's your gut feeling? Is your algorithm, is it a K approximation for some constant K or not?
No, I don't think that our 2-opt algorithm or heuristic approximates. So so in other words, maybe you can construct an example on which you can arbitrarily have an arbitrarily bad solution, for example. Maybe that's possible.
And you think the problem itself is K approximable for constant K?
Oh, okay. So it may be, of course, so again, if we look at this reduction from vector TSP to all of these TSPs, if we're allowed to visit maybe multiple times the same city, then maybe indeed it may be approximable. And so my gut feeling, as you asked, I would say, why not? Why would vector TSP not be approximable? It's close enough to other TSPs which can be approximated. So maybe this one can also be approximated.
Thank you.
So thank you, Ralf. So now Arnaud will say a few words about Jason.
Let me mute Jason.
I don't hear you.
Arnaud, we did not hear you at all.
I think I understand why now. my headset was not plugged. Okay, let me just start again. So I was just, yeah, there's an echo. So, okay. Oh, no echo. Okay, perfect. So sorry for that. So I just, I was saying I was not going to ask any question or comment the work, of course. I just wanted to thank a lot the members of the committee for attending the defense. And I wanted to say how sad I was that you are not here in presence, of course. And maybe I can tell to each of you remote members that your invitation ticket for the defense, you can use it afterwards. You'll be welcome here anytime. And and we can cover the expenses. So that's one point. Okay, more seriously, no, not more seriously actually. For the story with Eric, we have some bad luck with defenses, because I had to go to Le Havre in the last fall for attending a defense, and I eventually went there, but his daughter got the COVID and he was contact, and he could not attend the defense. So Eric, thank you for not coming so that my daughter don't get the COVID. It's okay. Anyway, no, more seriously now, a few words about Jason, because today is Jason's day. I wanted to say to you, Jason, how happy I am for these past few years, and you're such a lovely student. I spent a very nice time with you, and also I wanted to tell everybody that Jason is a very someone that you want to work with. He's a very nice, has a lot of curiosity, has a lot of ideas, and he's also a hard worker. So if all my students could be like this, I would just be very happy. So that's the only thing I wanted to say. And maybe also thanks the members of the committees for the nice questions that you've raised. Some of them I'm pretty sure we can discuss offline afterwards and in the following months altogether. So thank you, Jason, again. Yeah.
So now we'll have to finish this session. So just one question, because you had many questions. Did you take into consideration the standard kinetic data structures model about trajectory motion? I mean, if you consider a function of time as a definition, as a model of motion, is it possible to add this model in your software package easily?
So, so this question is with regards to the mobility models?
Yes.
Oh, okay. So I think the standard kinetic form of acceleration would be maybe as a double integrator, which is the one that was used in the other version of TSP, in which they added acceleration. And so I think this may be possible to add to the mobility models indeed, because even though it's a continuous nature model, I think JBOD-SIM would be able to simulate it. And again, it remains to be seen if this is indeed possible in JBOD-SIM.
Okay, so it was just a short question. So now the jury will deliberate, and for everybody, we can meet in 15 or 20 minutes, something like that. So yes, for the jury, we will switch to the other canal of Zoom. Maybe we can switch in 2 or 3 minutes if we can do a short break. So thanks a lot, everybody, and see you forward in 15 or 20 minutes.
Okay. So I will leave this session on, but I will mute myself so I cannot hear anything. So it's not here. It's
okay. So for Quentin, Rolf, and Paola, we will switch to the other Zoom link that I've sent. Before on an email. Okay. See you there.
1, 2.
Ok, je sais pas s'il y a des gens dans le coin, mais ça va pas tarder. Si ceux qui veulent revenir.
So everyone who is still here, we're going to start again.
Shall we wait 1 or 2 more minutes?
Est-ce que tu as bien raison?
Oui, peut-être juste pour la suite, s'il n'y a pas trop. Si ça presse pas. Allô? Pour demain? Nous allons plus en toi. Ok, excuse.
That was Flemish.
Voilà.
Bon, Jason, on voulait te remercier pour ton travail, ta présentation aujourd'hui, qui a été vraiment appréciée. Ton exposé, alors je ne sais pas comment me mettre. Ton exposé était vraiment très clair et pédagogique. Les illustrations étaient vraiment bien appréciées. Ça montrait vraiment du recul sur tout le travail que tu as fourni. Le jury a été convaincu de tes compétences aussi bien sur les aspects les plus théoriques, comme la construction des spanners, que sur les aspects d'implémentation et pratique. Voilà, donc ce large spectre, on ne le retrouve pas dans toutes les thèses, donc c'est vraiment appréciable. Pendant la session des questions, tu as répondu vraiment de manière très précise, tu as montré que tu avais une grande maturité, et pour toutes ces raisons, le jury te décerne le titre de docteur de l'Université de Bordeaux.
Merci beaucoup. Donc, je pense que je vais commencer par remercier du monde en français et peut-être tous les autres gens, je peux les remercier à la fin en anglais. Donc, merci beaucoup d'abord à Arnaud. Je préfère commencer par Arnaud parce que Arnaud m'a guidé au cours de ces 3 dernières années, même 4 si on compte le stage de master dedans. Et j'ai toujours été très content de travailler avec Arnaud. C'est un homme très sérieux, mais aussi très curieux, et très même créatif. Et donc tout à l'heure, il a dit qu'il aimait bien travailler avec moi parce que j'étais une personne curieuse aussi. Mais je crois fortement que c'est grâce à toi, Arnaud, que j'ai cette qualité aussi. Et donc j'espère que j'ai adapté quelques autres qualités de toi au cours des dernières années. Et peut-être réciproquement, en effet. Je ne sais pas, mais en tout cas, vraiment merci. Et j'espère que même dans le futur, à partir de maintenant, on pourrait travailler ensemble et même parler des sujets intéressants. Prochainement, enfin, après, j'aimerais remercier aussi le jury, bien sûr. Donc, le jury était très grand, composé de très bons chercheurs et dans des domaines très, très variés. C'était très appréciable d'avoir des questions des gens qui s'intéressent à des choses, même si c'est tout considéré dans l'informatique théorique, c'est quand même des domaines plutôt variés. Et j'ai beaucoup apprécié les questions et surtout aussi les questions un peu plus attaques. Je trouve qu'une thèse, ça se défend. Et j'ai bien aimé justement certaines questions qui mettent en question mes connaissances, mon intuition, ma capacité de répondre à ces questions-là. Après, bien sûr, j'aimerais remercier mes collègues. Et beaucoup d'entre eux, je les considère comme des amis. Ils sont sûrement en train d'écouter maintenant à côté dans des salles. Et aussi sur Zoom, il y a certains amis qui ne sont pas des collègues qui ont pu venir assister à cette soutenance. Je les remercie. À la fin, j'aimerais remercier Elodie, qui est très importante pour moi. Et je suis très content qu'elle a pu se libérer aujourd'hui pour être là, pour assister à cette soutenance. Et également, un grand merci à ses parents qui ont pu venir assister, même si je leur ai prévenu un peu tard peut-être. So the last thank yous will be given in English for a few people who may not speak French. So thank you very much. So probably the jury members who may not be French natives. Thank you very much for the interesting questions and for the fact that you were here to listen to my presentation. It means a lot. Thank you very much.
Bon ben, ainsi se termine la soutenance de Jason. Donc malheureusement, nous ne pourrons pas trinquer ensemble. Peut-être que Jason enverra des bouteilles à tout le monde.
Oui, c'est prévu.
Surtout pour le jury qui n'a pas pu venir. So thank you very much for attending to this defense. And so we hope to see you in Bordeaux, maybe in 2 or 3 years. COVID. Oh, maybe before. So have a good day and see you.
Thank you.
Congratulations.
Thank you very much.
Congratulations.
Bravo.
I'm going to take this off of the big screen and off of the big speakers. So anyone who wishes to say something, you can do so freely in just a couple of minutes.
Okay, merci Paola. Thank you, Rolf. Thank you, Quentin. Thank you, Eric.
Thank you.
Bye.
Congratulations again.
Congratulations again, yes. And I hope you'll have some friends, some good friends